friends, today we will discussing about ECG concept or electrocardiogram concept, and the concept contains the cardiovascular action potential. So we only know about the cardiovascular action potential. We will discussing only this for today. I will make several videos about this electrocardiogram concepts. So let's start. We know that heart is a very important organ of our body. In higher animals, heart is very important. It's expensive than gold even. Okay, heart is very important. And the heart, a human heart and other animal heart have a common structure like this. And heart, mainly heart consists of atrium. If I imagine this as a human heart, then heart consists of atrium and a ventricle, two ventricles and two atriums. Okay, and the heart is mainly consist of cardio muscles, that is cardiac muscles. Okay, so cardiac muscles are made up of cardiomuscular cells. Cardiomuscular cells produces electrical impulses from action potential. But what is action potential and what is the source of it? I will say you. So what is ECG? The full form of ECG is electrocardiogram. It is a device, or it is a graph also. ECG machine acts or works on a principle of galvanometers that measures the electrical potentials produced by the cardiomuscular cells. So let's start about this cardiovascular action potential. So ventricular muscles are very thick and atrium muscles are very thin. I magnifying the muscle cells and I draw it in very big size. Okay, the cardiomuscular cells contain several proteins, membrane proteins. They contain some sodium channels, or calcium channel. They are leaky channels. That means they are non-gated channels. They are always open, so they are called non-gated channels. But there is some condition there, and it is called voltage gated sodium channels. Voltage gated sodium channels, and these channels are some are potassium channel and some are calcium ion channel. Okay, so basic concept of the cardiomuscular cells is the cardiomuscular cells contain several membrane proteins. The membrane proteins are calcium ion or sodium ion leaky channels or non-gated channels, and some voltage gated Na plus or sodium channels, and some calcium ion and potassium ion channels. And they also contain sodium potassium pumps also. Okay, it's the basic structure of a cardiovascular cell. So when a specific stimulus that stimulates the sodium and calcium leaky channels or non-gated channels. This stimulus activates the calcium channels and non-gated. Before this stimulus, the internal membrane is negatively charged always in the cardiovascular cell. The internal membrane is always negatively charged. The potential in the cell is minus 90 millivolt. Okay, minus 90 millivolt potential in the cell. So these cells are in resting state. Okay, these cells are in resting state. They are constant. This minus 90 millivolt is constant for a several time. But when a stimulus stimulates the sodium ion channels and calcium ion channels, then the sodium and calcium leaky channels or non-gated channels activates, and they transports sodium and calcium ions that are positively charged inside the cell, or they transports the sodium and calcium ions from the outside to the inside of the cell. Okay, so the sodium ions now and calcium ions now starting to flow inside the cell, and the inside of the cell becomes positive, and gradually the positive nature is increasing with the flow of sodium and calcium ion in the cell. So the negative nature, that was the resting state, that is minus 90 millivolt state, that is negative polarized state, is lost because the positive charged ions gradually flows inside the cell, and the positive charge neutralizes the negative potential in the cell. So the negative charge decreases in the cell by these ions, positive ions. So the membrane potential gradually becomes positive, and it's a point like 80 minus 80 millivolt increasing, but the negative value is decreasing because the positive charged ions flow inside the cell. So the positive ions, the positive charge neutralizes the negative charges in the cell. So the negative charge decreases in the cell and the positive charge increases in the cell. 80 and minus 70, and this minus 70 is very important for this cardiovascular action potential, because the minus 70 millivolt, this potential is called threshold potential. This potential, when the cell reach in this potential, then the voltage gated sodium ion channels activated, and the sodiums flow inside the cell from the outside very rapidly. This minus 70 millivolt value of the membrane potential, that is also called threshold potential, activates the voltage gated sodium channels that moves or transports sodium ions from outside to the inside of the cell in very rapid rate. Okay, so the inside of the cell rapidly become positively charged, and the positive charge in the cell gradually or rapidly increasing. So at last the increasing value minus 70, minus 60, minus 50, minus 40, and at last the value is reached to 0, and then plus 10 millivolt. In plus 10 millivolt, the plus 10 millivolt, in this membrane potential, the calcium ion channels and potassium ion channels are activated, and the potassium ion channels, through the potassium ion channel, we know that every healthy cells are rich in potassium ions. Okay, every healthy cells are rich in potassium ions. So the extracellular potassium concentration is less than the intracellular potassium concentration. So potassiums flow outside by the potassium channels along its concentration gradient. Okay, potassium channels facilitates the diffusion of K plus ions, and you thought that the K plus ions released from the cell, so the cell now become negatively charged further, but that not, because there are some calcium channels also. Calcium channels works the opposite process. The calcium concentration of the extracellular environment is greater than the intracellular environment. Calcium ions started their transport along its concentration gradient. So we know that calcium ion concentration is very higher in extracellular environment but very lower in the intracellular environment. So calcium ions diffused by the calcium ion channels, and calcium flow inside the cell, but potassium ions flow outside the cell. But there is a special term that in that is when the membrane potential reach to plus 10 millivolt, then the potassium ion channels are activated fast. Okay, potassium ion channels are activated fast, so potassium ions rapidly moves towards the outside of the cell, so the cell gradually becomes further negative, so the graph further moves down, but suddenly the calcium ion start working, and the calcium ions moves inside the cell from the outside, and you saw that calcium ion and the potassium ion moves towards the opposite direction, and the opposite transport or opposite flow of these two ions creates a equal potential. Okay, it's make a constant potential, because one positive charge becomes inside and one positive charge become flow outside, so the membrane potential remain constant for a some time, remain constant. Okay, remain constant because I repeating this time calcium, this point, when the membrane potential reaches to plus 10 millivolt, the potassium ion channels start their working fast. Okay, then that time the cell intracellular cytosol become further negatively charged, because the positive charged potassium flow outside the cell, but suddenly the calcium ion channels also activated. So the calcium ion channels transport in the opposite direction of the positively charged potassium ions. So this type of transport of calcium and potassium channels at the opposite direction constant the membrane potential for some time. So the membrane potential remains approximately constant for this time, but suddenly the calcium ion stop their working. So the calcium ions stops their flow inside the cell, but potassium ion channels still working, and they become more active than the initial phase. So more potassium ions moves towards this potassium channel. So potassium releasing process increases. So the cell rapidly lost their positive charge in the cytosol, and they return to their initial phase and further reach to the minus 90 millivolt again. Okay, the calcium ion channels stopped their working, so the calcium ion cannot transport into the cell, but potassium ions still working. Potassium ion channels still working, and they transports the potassium ions outside the cell. So the intracellular cytosol becomes negatively charged again, because the positive charge moves outside the cell. So the cytosol becomes negative again. So the graph suddenly down, and they reaches their initial membrane potential, that is 90 millivolt, and the cycle is continuous. This cycle is continuously. Okay, it's the end. Now the main thing. Okay, in this case the membrane potential becomes positive, minus 90 millivolt to plus 10 millivolt. In this case the membrane potential becomes positive and increases. This case is called depolarization. But in this case the membrane potential become negative again and become minus 90 millivolt again. This curve of the graph is called, and this process is called repolarization. It's called repolarization. Okay, and the depolarization and repolarization processes continuously happened and creates a action potential. Okay, this depolarization and repolarization together form a action potential, that is a movement, a relative movement of ions in cells that creates a action potential. This full process with the depolarization and repolarization is called action potential. Okay, this is the whole process in one cardiovascular cardiovascular cell. Okay, but in this case it is the first cell. We imagine it is the first cell that is affected by the stimulus. Its stimulus but in this cell this cell not need any stimulus, because the stimulus regulates the flow of cations inside the cell, these positively charged cations. moves to the second cell by a special type of protein junction that is called gap junction. So the cardiovascular cells attach to another adjacent cells by gap junctions. Gap junctions are made up of connexin proteins that form a connection protein. Connexins looks like this. This 6 connexin subunit like this, okay, like 6 subunits. Each subunit called connexin, and the whole protein is called connexon. Okay, sorry, it's connexin, double N. Okay, so here the connexons are electrical doors that are regulated by the membrane potentials and the cations that was flow outside inside the cell by the stimulus action that can further enter into the second cell. The calcium ions and the sodium ions transport through the gap junction to the another cell, and this ion do the same case like this. Okay, and the cell to one cell to another cell and to another cell, the same thing is happening, and the membrane potential goes throughout the cell to cell. This full process is called cardiovascular action potential. Okay, our heart contains some special nodes, SA node, AV node. SA node is called pacemaker of our heart. So they also contains the specific cardiovascular cells. Okay, we imagine that a small piece of the ventricular muscle tissue represent here in a large size, in big size. Okay, a small piece of cardiac muscle from a heart. Okay, imagine it is A point, it is B point, and we feed a galvanometer with this. That shows a 0 reading. Okay, it's a different part. Okay, we assemble a galvanometer that is wired in two corners of the small piece of cardiac muscle, and cardiac muscle is connected with a galvanometer, and we imagine that it is plus point of the galvanometer and it is the negative point of the galvanometer. Okay, now imagine that special stimulus is used in A position. Special stimulus is act in A position in the small piece of the cardiac muscle cell, and this cardiac piece of sheet, and this sheet contains many cardiac muscle cells, many. Okay, so because the stimulus act here in this A side, so we know that in previous section that the stimulus causes the depolarization of the cardiovascular cells. So the cell become positively charged for a small amount of time. Okay, so cells are positively charged, and we know that the one cell depolarization causes the another depolarization of the adjacent cell, and then the cell that have the depolarization that causes the another depolarization in their adjacent cells. So these cells also depolarized by this. Okay, and these also polarized by the effect of the adjacent cells, but these are not polarized for this time. Only for some time these are not polarized presently. Okay, so we can tell that this position the cells have 90 millivolt, because in this position the cells are in resting state, so it's minus 90 millivolt. But this position they gain their intracellular charge in positive charge. So the galvanometer senses potential difference between the 2 points A and B. A point is positively charged and B point is negatively charged. So the galvanometer shows a reading, but which reading, positive or negative reading? The plus charge is always moves towards the positive electrode of the galvanometer, because the cells are negatively charged, but these cells are positively charged. So the positive charge moves towards the B point or the positive electrode of the galvanometer. If positive charge moves towards the positive electrode of the galvanometer, then the galvanometer always shows a positive value. Okay, and the galvanometer always shows a positive value. Its neutral value is it's 0. This can be 40 volt. Imagine 40 volt plus 40 volt. Okay, but it's occur for a depolarization. But when in second step, it's first step, when this in second step all cells are depolarized equally, then all cells are, we know that the positive charge spread from the A side to the B side. So at last the whole muscular tissue cells become positively charged for the depolarization effect. Okay, whole membrane is now positively charged, whole muscle cells are positively charged. So now the galvanometer shows a special reading, A side, B side. Okay, because the every cells A side and B side all are same charged, all are positively charged of a same amount. All cells are positively charged, so here is no potential difference to sense. So in this point galvanometer shows a neutral reading, 0 millivolt or 0 volt. Okay, It's the electrode only, it's not charge, it's electrode sign. For the depolarization, the stimulus affect the first these four cells, then the four cells affect adjacent cells, and the adjacent cells also become positively charged, and they also transfers their charge to the adjacent cells. So the cells gradually becoming positive, but this point they are half positive and half negative, because these cells are not affected now for the stimulus. So the cells still charged by resting potential, that is minus 90 millivolt, but this point is positively charged. So galvanometer sends a potential difference between 2 points A and B, but when the positive charge spread in all cells equally, the galvanometer shows zero value, zero reading, because all cells are same charge. So galvanometer don't sense any or cannot sense any potential difference between A and B point. In third step, all cells are now positively charged, we know, okay, that the galvanometer cannot sense the potential difference in this system. So galvanometer was showed the zero reading, but it's the time for repolarization. In repolarization occurs the repolarization of the cells always occurs at the plus electrode side, okay, always occurs at the plus electrode side of the galvanometer. So in repolarization the cells become negative again, that is minus 90 millivolt. That means they return to their normal resting state gradually. So in this case, imagine that the minus charge is going towards the negative electron of the galvanometer gradually, that is at its A side. So the positive charge or negative charge move towards the negative electrode of the galvanometer. So if the same charge goes to the or moves towards the same electrode of the galvanometer, then the galvanometer always shows the positive value. So in this case also the galvanometer shows a positive value. It's neutral, it's positive value. Shows a positive value. Okay. And at last all cells will become negative. Okay, at same just all cells become now negative, and now galvanometer have no any potential difference for sensing. For this case, galvanometer shows zero reading again, because there are no any potential difference between A and B. Okay. By this concept, our heart or cardiovascular cells have a electrical activity or a potential activity or a action potential, that is called, that can be measured by any galvanometer. But what is the relation between galvanometer and ECG? I will say you in next video. So it's enough for today. Goodbye.